In this video, we will be making a calibration curve in Excel to find an unknown mass fraction. The calibration curve is a graph which gives the relationship between one type of measurement and another. Since the mass fraction, which is a unit of concentration, is related to the density of the solution, we can graph a few data points for solutions for which we know both the mass fraction and the density. We'll be graphing data for 4 different solutions, A, B, C, and D, which each have different mass fractions and corresponding densities. The equation for the line that fits those data points will tell us the relationship between the mass fraction of any fructose solution and its density. If we know the density of an unknown solution, we can find its mass fraction using our calibration curve. Mass fraction is calculated based on how each solution is made. You are weighing out different amounts of fructose for each solution. For example, for flask A, you are asked to weigh out approximately 0.65 grams of fructose. You should report all digits from the digital scale, which in our case reads to 4 digits after the decimal. For example, you might measure 0.6545 grams for flask A. To calculate mass fraction, take grams of fructose measured on the scale and divide by the volume of solution you are making. You are using 25 milliliter volumetric flasks to make your solutions, so the volume of each solution is 25.00 milliliters. 0.6545 grams of fructose divided by 25.00 milliliters gives a mass fraction of 0.02618 grams of fructose per milliliter of solution for flask A. In the video titled Graphing in Excel to Find Density, I have gone through the steps of graphing mass and volume data to find density of a solution. Remember, density is the slope of a graph of mass versus volume. You should have followed the steps from the video to create 5 different graphs, one each for flasks A, B, C, and D, plus one for a solution of unknown concentration. In order to make our calibration curve, we will use the densities of flasks A, B, C, and D, along with the values we calculated for the mass fractions of flasks A, B, C, and D. As you may recall, the x-axis data goes in column A in Excel, and the y-axis data goes in column B. In this case, I want mass fraction on my x-axis, so I place my mass fraction data in column A. Cell A1 contains my heading, mass fraction in grams of fructose per milliliter, and cells A2 through A5 contain my mass fraction data, 0.02618, 0.05102, 0.1001, and 0.1405 grams of fructose per milliliter. Those values are the mass fractions of solutions A, B, C, and D, respectively. I want density on my y-axis, so I place my density data in column B. Cell B1 contains my heading, density in grams per milliliter. And cells B2 through B5 contain my density data, 0.9797, 0.9839, 0.9924, and 0.9997 grams per milliliter. Those values are the densities of solutions A, B, C, and D, respectively. I have already created my graph using the same methods used in the video titled Graphing in Excel to Find Density. The equations for my trend line and my r-squared value are already displayed on the graph. Since the trend line on my graph is linear, the equation on my graph is in the general form y equals mx plus b. M is the slope of the line and is the number to the left of the x. In the equation on my example graph, my slope m is equal to 0.17486. It is important to note that the slope of this graph does not give a density value, because this is not a mass versus volume graph. B is the y-intercept and is the number to the right of the x, including a minus sign if present. In the equation on my example graph, my y-intercept, b, is equal to positive 0.97503. The r-squared value tells me how well Excel's line fits my data. Since I have fit my data to a linear trend line, it is telling me how close to perfectly linear the data are. The closer the value is to 1, the better the fit. Since you will be working with real data, you should not expect your value to be exactly 1. It may be slightly less, like mine, which is the 0.99983 shown on my graph. Once you find the density of the unknown solution, which is the slope of the mass versus volume graph of the unknown solution, you can plug that value in for y in the equation for your calibration curve. We plug it in for y since our graph has density on the y-axis, due to it being the dependent variable. We need to rearrange the equation to solve for x, which is the mass fraction of the unknown solution. Notice that we have mass fraction on the x-axis because it is the independent variable. Let's say our graph of mass versus volume of the unknown solution had a slope of 0.98562, corresponding to the density of the unknown solution. In my example calibration curve, my equation is y equals 0.17486x plus 0.97503. I plug in my density value for the unknown and get 0.98562 equals 0.17486x plus 0.97503. To get x by itself, I subtract 0.97503 from both sides and divide both sides by 0.17486. My rearranged equation becomes x equals 0.98562 minus 0.97503, all divided by 0.17486. And I get 0.060563 grams of fructose per milliliter of solution as the mass fraction of the unknown solution.